Welcome back to Chibuzor Mathphysics. In the previous video, we were talking about linear wave equation, and we talked about how we can describe such a wave equation. Of course, we know it is given by 1 divided by v squared, the second partial derivative of x in respect to t, and that must be equal to the second partial derivative of y in respect to x. We proved that indeed that is equal when we got 1 divided by lambda squared to be on the left hand side, which was equal to the 1 divided by lambda squared, which was on the right hand side. So in today's video, following up on that proving, we are to show that the displacement of the particle at a distance x from O is given by y is equals to a sine 2 pi into t divided by the capital T minus x divided by lambda. You will recall that, as I mentioned earlier, y is nothing but the vertical displacement or the vertical direction of this particular wave, and a is nothing but the amplitude. T in this case helps us to know the time taken. The capital T represents the period, x represents the horizontal position, and lambda will be given. We know what lambda is. It is given in terms of wave equation. So we are going to be proving this, and it is good to pay attention to details, as it will help us to know how to we got to this point. As you might also have noticed, this particular equation is for a progressive wave. The one that we did earlier on help us to understand transverse wave. A progressive wave oscillates the particles of the medium it is traveling through, while a transverse wave has oscillation that are perpendicular to the direction of energy transfer. So this is a progressive wave, and we are going to prove that indeed y is equals to a sine 2 pi into t divided by t minus x over lambda. So let us recall. You might recall that we know that y, we have said that y represents the vertical position. So we are going to be proving that using this equation, y is nothing but a sine we're going to have omega t minus phi, which is the phase angle. So this is what we are going to be using to prove this indeed. Let's make this pen more bright. Good. So this is what we have, and we are going to prove that indeed this is actually true. Okay. So we can call this equation 1. If this is equation 1, you can recall from the simple harmonic motion. We know that from the simple harmonic motion, omega is nothing but 2 pi f. 2 pi f. This is omega, and we know also that phi, which is the phase angle, is nothing but 2 pi. This is 2 pi x over lambda. So we have to replace this in this given equation. If we replace that in the equation, what we now have is y is equal to, y will be given by we have a sine. Now in the place of omega we have 2 pi f, so it is 2 pi f minus phi, which is the phase angle, is 2 pi x over lambda. So this is what we have. But you see now we have 2 pi, we can actually factor out 2 pi. If we factor out 2 pi, let's factor out 2 pi. If we do that, y becomes a, then we have a sine 2 pi, a sine 2 pi. What is left inside is nothing but ft. Of course, we still have t because this is omega t, so there is t here. So this is ft minus. We factored out 2 pi, so we are left with x over lambda. X over lambda. Now we know also from wave equation that v is given as lambda f. V is nothing but lambda f, and to find frequency, Vf can be represented in the form of v over lambda. So let's go ahead to replace this. I want us to replace this. Replace this in this equation. Let's replace f, which is v divided by lambda, into this equation, so that we have y to be a sine 2 pi. In the place of f, we will have v, so it becomes vt, because we have vt, so it is vt over lambda, like we have here, and minus, what do we still have there? It is x over lambda. We want to put indeed this is the given wave equation for a progressive wave. Okay, of course what we are proving is that y is equal to a sine of 2 pi. Then in our bracket we had the small t over capital T minus x over lambda. So this is what we want to show. Okay, at this point we know that we can actually factor out something else. We have a sine 2 pi vt over lambda minus x over lambda. We can factor out lambda if we want. If we factor out lambda, we'll have y is equals to a sine of 2 pi over lambda if we factor out lambda, and then we are having vt minus x. And we know we can actually call this equation 2. We know that v is nothing but the wave speed, x is the horizontal displacement. So if v is the wave speed, it means that we can actually rewrite this to be a sine of 2 pi. We factored out lambda. But let's assume we still have our lambda in, so this becomes v. This is a small t over the period, since v is the speed, the wave speed or the displacement, minus x over what you will have is lambda. That is, if you allow this lambda remain inside. Of course, if you observe, you will note that our equation says that a sine 2 pi into t divided by t minus x divided by lambda. But this equation can be written as y is equals to a sine 2 pi over lambda, like I did earlier, into Vt minus x. It is actually the same thing, but I just wanted you to see how we got this and this to be the same. V is the speed of the wave. It shows us the speed of that wave. X is nothing but the horizontal direction. Of course, this t is nothing but it shows us the period of the wave, and it can be seen as v, which is the speed of the wave. That's why it is t over t, which can be Vt minus x divided by lambda. And by doing this, you have shown that indeed a particle of a medium in a progressive wave traveling along the position x axis, which is the horizontal position, is situated at a point P. And if it is situated at point P from O is the origin, then we can say that y is equals to a sine 2 pi into t over t minus x over lambda. I hope you get what we have done there. We are going to use these equations in our next video for computations. I hope you have enjoyed the video. We will catch you in our next video. My name remains Austin Garagash.